Welcome. In this outcome, we'll build a picture of the atom from the inside out and see how the arrangement of its electrons explains an element's properties and where it sits on the periodic table. Let's begin. Let's start with the basic architecture. At the center of every atom sits a tiny, incredibly dense nucleus, and packed inside it are the protons and neutrons, which together we call the nucleons. The electrons occupy the space around that nucleus in shells, and here's the striking thing. The atom is almost entirely empty space, with nearly all its mass crammed into that central core. Because the positive and negative charges balance, the atom as a whole comes out electrically neutral. Now let's compare the three particles. The proton and the neutron both sit in the nucleus, and each has a relative mass of 1. The proton carries a charge of +1, while the neutron, as its name hints, is neutral, with no charge at all. The electron lives out in the shells, and it carries a charge of -1. Its mass, though, is tiny, only about 1/1836th of a proton, so for most purposes, we treat it as very nearly zero. A few terms worth locking down. The atomic number, given the symbol Z, is simply the number of protons in the nucleus, and it's what defines the element. The mass number, symbol A, is the total count of protons and neutrons together. Any particle in the nucleus, proton or neutron, is a nucleon, and isotopes are atoms of the same element, so the same Z, but with different numbers of neutrons. Let's tie those numbers together. The atomic number Z is the number of protons, and in a neutral atom, the number of electrons matches it exactly. The mass number A is protons plus neutrons, so if you want the number of neutrons, you just take A minus Z. We write these on the symbol with the mass number on top and the atomic number below, so sodium appears with its mass number on top and its atomic number 11 underneath. Let's work one through. We've got an atom of chlorine written with mass number 35 and atomic number 17. The atomic number is 17, so straight away, that's 17 protons. Because the atom is neutral, the electrons match the protons, so 17 electrons too. For the neutrons, we do A minus Z, that's 35 minus 17, which gives 18. So the atom has 17 protons, 17 electrons, and 18 neutrons. Let's look more closely at isotopes. They share the same atomic number, but differ in mass number, and the only thing that changes is the number of neutrons. Take chlorine. Chlorine 35 has 18 neutrons, while chlorine 37 has 20. Crucially, their chemical properties are identical, because chemistry is governed by electrons, and the electron arrangement hasn't changed at all. Physical properties like density do differ a little, since the atoms have slightly different masses. Now we zoom in on where the electrons actually sit. They're held in energy levels called shells, numbered N equals 1, 2, 3, 4, and so on as we move outwards. Each shell is divided into subshells, labeled S, P, and D, and those subshells are themselves made up of orbitals. An orbital is just a region of space that can hold up to 2 electrons. And as a rule, the higher the shell, the further out it lies and the higher its energy. Let's put some numbers on the subshells. The S subshell contains a single orbital, the P subshell has 3, and the D subshell has 5. Since every orbital holds 2 electrons, that means S holds 2 electrons in total, P holds 6, and D holds 10. Those figures, 2, 6, and 10, are worth committing to memory, because they underpin everything about how electrons fill up. Electrons are economical. They always fill the lowest available energy first. The order goes 1s, 2s, 2p, 3s, 3p, then 4s, and only then 3d. And that's the one that catches people out. 4s actually fills before 3d, because 4s is slightly lower in energy. Each orbital takes its 2 electrons before the next begins, and following this order, builds up the full electronic configuration, which in turn explains the shape of the periodic table. Let's write out sodium's configuration. Sodium has an atomic number of 11, so 11 electrons to place. We fill in order: 1s, 2s, 2p, then 3s. So 1s2 takes us to 2 electrons, 2s2 takes us to 4, 2p6 brings us to 10, and the last electron goes into 3s, giving 3s1. Putting it together, sodium is 1e2, 2a2, 2p6, 3s1. Iron is a good test because it involves that 4s before 3d rule. Iron's atomic number is 26, so 26 electrons. We fill 1s, 2s, 2p, 3s, 3p, then 4s, and finally 3d. So 1s2 gets us to 2, 2s2 to 4, 2p 6 to 10, 3s 2 to 12, 3p 6 to 18, 4s 2 to 20, and then 3da6 brings us up to 26. So iron is 1, s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Let's pause and check your understanding. First, can you write the full electronic configuration of chlorine, atomic number 17? Second, how many electrons can a full p subshell hold? And third, why does 4s fill before 3d? Have a proper think about each before you carry on. Now we turn to ionization energy, a beautifully revealing quantity. The first ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms. We write it as X gas goes to X plus, gas plus an electron. It's always an endothermic process, energy in, because you're pulling a negative electron away from a positive nucleus that wants to keep it. It's measured in kilojoules per mole, and it tells us how tightly the atom grips its outer electron. So, what decides how big that ionization energy is? 3 factors work together. First, nuclear charge. More protons pull the electrons in more strongly. Second, distance. An electron further from the nucleus feels a weaker pull and is easier to remove. And third, shielding. Inner electrons get in the way and reduce the pull felt by the outer ones. The stronger the net attraction, the higher the ionization energy. And these 3 factors explain every trend we'll meet. Let's define these carefully. First, ionization energy is the energy to remove 1 electron from each atom in 1 mole of gaseous atoms. Nuclear charge is the positive pull of the protons on the electrons. Shielding is the way inner shell electrons reduce that pull for the outer electrons. And successive ionization energy is the energy for removing each further electron, one at a time, from an increasingly positive ion. Here's a powerful idea. We can remove electrons one at a time, and each removal has its own successive ionization energy. These values always increase, the first smaller than the second, which is smaller than the third, and so on, because you're prizing an electron away from an ion that's getting more and more positive. But watch for the big jumps. A sudden large jump appears when you start breaking into a new inner shell, and those jumps reveal exactly how the electrons are arranged in shells. Let's read some real values. The first 4 ionization energies of an element in kilojoules per mole are 578, 1817, 2745, and then 1177. We're hunting for a large jump. The first 3 rise fairly gently, 578, 1817, 2745, but the fourth, 1177, is an enormous leap upward. That tells us the fourth electron is being torn from a new inner shell, much closer to the nucleus. So 3 electrons come away easily from the outer shell, which places the element in group 3, aluminium being the classic example. Let's explain a jump using sodium, which is 1s2, 2s2, 2p6, 3s1. Why the large jump between its first and second ionization energies? The first electron comes from the outer 3s subshell, out in shell 3. It's far from the nucleus and well shielded, so it's relatively easy to remove. But the second electron has to come from the 2p subshell in shell 2, much closer to the nucleus and far less shielded. That takes a great deal more energy, and the size of that jump tells us sodium has just 1 electron in its outer shell, marking it out as group 1. Now, the trends. Across a period, first ionization energy generally rises. That's because the nuclear charge increases while the shielding stays roughly the same, so the outer electrons get pulled in more and more strongly. It isn't a perfectly smooth climb, though. There are small dips, for instance, going from group 2 to group 3, and those little dips are actually valuable evidence for the existence of subshells within a shell. Down a group, the trend runs the other way. First, ionization energy falls. Each element down the group has an extra full inner shell, so the outer electron sits further from the nucleus. That greater distance, together with the increased shielding from those inner shells, weakens the net attraction. So the outer electron is held more loosely and lost more easily the further down the group you go. Let's connect this to the layout of the table. A group is a vertical column, and elements in the same group share the same number of outer electrons, which is why they behave so similarly in reactions. A period is a horizontal row, and the period number tells you the outer shell number, n. So an element's position on the table links directly back to its electronic structure. The periodic table is also carved into blocks, according to which subshell the outer electron goes into. In the S block, that outer electron enters an S subshell, and that's groups 1 and 2. In the P block, it enters a P subshell, covering groups 3 across to group 0. And in the D block, it enters a D subshell, and those are the transition metals. So the block simply tells you which type of subshell is filling last. Let's see that with 3 examples. Magnesium ends in 3s2, so its outer electron is in an S subshell, placing it in the S block, group 2. Chlorine ends in 3p5, a P subshell, so it's in the P block, group 7, and iron ends in 3d6, 4s2, with a D subshell filling, so it sits in the D block as a transition metal. Read the ending of the configuration and the block falls out. Let's predict a full position from a configuration. We're given 1s2, 2s2, 2p6, 3s2, 3p4. The outer shell is n equals 3, so it's in period 3. The outer electrons are in 3s and 3p, and 2 plus 4 gives 6 outer electrons, which means group 6. The last electron enters a P subshell, so it's in the P block. Put that together, period 3, group 6, P block. And you've identified sulfur, atomic number 16. Time for another check. First, can you write an equation for the first ionization energy of magnesium? Second, can you explain why first ionization energy falls as you go down group 1? And third, where would an element ending in 4s2, 3d3 sit in terms of its block? Work through those before we wrap up.